last time we talked about distance functions, and then we talked about two requirements. One is distance functions has to be representative of the semantic notion of similarity. So I give you a couple of examples, right? When you compare two data points, the comparison has to be relevant to the context of the problem. So for example, let's say last time we talked about the YouTube video, video recommendation algorithm. So when you recommend a video, then you need to somehow evaluate the similarity between the videos. And when you do that, there can be many different metrics to compare two videos per se. So for example, you could, simply just decide to take the average, RGB pixel values of a video over time and just compare the distance between the average RGB pixel values. Obviously, it's going to give you some, measure of distance, but in the context of video recommendation algorithm, it's not a very good distance metric, obviously, because it doesn't really represent the notion of similarity, right? When people gets a suggestion from an algorithm, they would expect the suggestions are based on the contents rather than what is the average color of the pixels, right? So in the context of the problem, the distance function is not so useful. So the first requirement is that the distance function has to be representative of the semantic notion of similarity in the context of that problem. So that was the first requirement. And then the second thing was that, technically, so, there are some mathematical conditions that a distance function has to satisfy. So these are four requirements mathematically in terms of, what a function must satisfy in order to become a distance function. So we talk about non-negativity. So we cannot have a distance function that has a negative value. So we're not going to allow negative distance. And the second condition is isolation. So, in this non-negativity constraint, the equal sign only happens when the two data points are identical. Okay, so so that's the condition for isolation. And then the another condition is symmetry. So distance from x to y has to be the same as the distance from y to x. So that's the symmetric condition. And then finally, there's a triangle inequality condition, which says when you take a detour, so instead of going straight from x to y, if you take a detour and then visit z first and then go to y, then the detour is going to take longer than going straight from x to y, unless z is right in between x and y. Okay, so those are the conditions that a distance function must satisfy. Now, based on that, there can be a lot of different distance functions. And, given a distance function, now you can have a data space, which can be called as a matrix space. Okay, so metric space means the mathematical space, the feature space, is equipped with some distance function. Okay, so that's kind of a technical setting to define a mathematical space for a data distribution. Now, in some scenarios, as opposed to distance function, you may want a similarity function. So distance functions, they have a greater value for dissimilar objects. So when the objects are similar to each other, then the value is going to get closer to 0. Otherwise, the distance function will have some large value if the objects are not so similar. Now, in contrast, similarity function is kind of the opposite. You want to have a large value for similar objects, and you want to have small values for dissimilar objects. So usually large means close to 1 and small means close to 0. That's kind of a usual formulation. Of course, you can go with your random range, but typically when the two objects are identical, then you expect the similarity value of 1. And then when the two objects are dissimilar, then the similarity function is going to go near 0. Okay. So there are a lot of different ways of treating this problem. First thing is simply just, take the negative of the distance function. So dxy is a distance function. In this case, we, assume that we're normalizing this to be in between 0 and 1, so that by taking 1 minus the distance function, you can have the values ranging from 0 to 1 in a opposite direction to the distance function. Or this is actually a slightly more favored way, because there are some outliers, and because of those outliers, the way that you normalize the distance function is not going to be very stable. So what is better is to use the property of an exponential function. So exponential function, if you take the exponential of a negative of distance, then you can guarantee that the values are always greater than 0, which in the previous case we couldn't guarantee that, right? And then depending on the way that you normalize this function, obviously you can set it to between 0 and 1. So no, sorry. Well, that was my mistake. When the distance is 0, then that means the exponent is 0. So e to the 0 is 1. So obviously when distance is 0, then we have the value of 1 automatically. And then when you have a large distance, then that means we have negative of d. So the curve is going to get closer asymptotically to 0, right? So that's what happens with this exponential formulation. So usually people just simply convert a distance function to a similarity function by taking the exponential of the negative of the distance function. Okay. So I'm pretty sure you're already quite familiar with these type of distance functions. So these are the most common type of distance function. So you probably are familiar with this Euclidean distance, right? So when you represent two different objects as x and y, okay, those are not coordinates, those are different objects. And then each of the objects are represented by coordinates, right? So assuming that we have d dimension, then we're going to have, well, in this notation, for some reason, we're using m to annotate the dimension. So then in that case, this, you found this, very familiar, where you take each of the components and then find the difference between each of the components, take the square of them, and then, after taking the summation of all the squares, you take the square root, right? And that's what is called a Euclidean distance, right? So that's a definition of a Euclidean distance. Now, what is called the LP norm, or Minkowski distance, is a generalization of Euclidean distance, okay? So P over here is the parameter. When P equals to 2, this becomes a Euclidean distance. So simply just, substitute P with 2. You'll realize this is exactly the same formula as the one that I just have written down, the Euclidean distance formula. When P equals to 1, it is called a Manhattan distance. When P equals to 1, then the square root part goes away, and then it becomes just an absolute difference between the coordinate values. So the reason why this is called a Manhattan distance or a city block distance is because, if you think about it, if you, visit New York, the Manhattan is basically like, a bunch of streets and avenues, east to west and north to south, right? And then from one location to the other location, there's no way that you can go directly from, one point to the other. You have to follow the roads, right? Whichever way you take, you have to follow the roads that are in a grid shape. And if you think about it, in this case, we're going 1 and 2 times to the right. And then we're going 1, 2, 3, 4 times to the top. So the distance in this city block is basically 2 to the right plus 4 to the top, right? So then in that case, assuming that, each of the grid are the same size, then the distance from this location to this location is going to be 6. So that's why this thing is called a Manhattan distance or city block distance. So that's one way of comparing distance between two objects. And like I said, when P equals to 2, it's a Euclidean distance. So this is probably the one that you guys are most familiar with. You can increase P and decide to go with P equals to infinity. And if you take the limit, right, you send the P to infinity, then what happens is this gets closer to 0. and this one gets closer to infinity. Okay, and then applying the things that you learn from calculus, you will realize this actually converges to this value as p goes to infinity, which is the maximum of the difference among the component, each individual components. Okay, so let's say we have 2, 4, 3. That's my object x, and then here's another object 1, 0, 4. Now, if you compare the difference between the objects, then the first component we have 2 minus 1, which is 1. The second component, the difference is 4, and then the third component, 3 and 4, the difference is 1, right? And then among them, the maximum difference is 4 over here. Okay, so that's going to be the L infinity distance between the two objects x and y. Okay, so those are kind of quite trivial mathematical distribution, and if you have some guarantee that your objects are represented in a vector space, then you can simply choose a Euclidean distance, or for the sake of computational time or whatever reason, you can use some other generic Minkowski distance. Okay. For the cases where we don't have that nice vector representation, we're going to talk about it very soon. But in such cases, Minkowski distances are not quite suitable, obviously. Now, at the end of the day, what we're interested in constructing is what is called a distance matrix. Okay. So from a data matrix or a feature matrix, where each of the rows represent an object, and then each column represent a feature vector, a feature of that object, okay? And from there, you want to produce a distance matrix, okay? So there are many ways of computing this. In case of Euclidean distance, if you think about it, this is just a quadratic function of this feature matrix. In case of the Manhattan distance, you simply just calculate the absolute difference between the rows, and then using that to you can construct a distance matrix. But at the end of the day, the distance matrix is going to have a form of a symmetry matrix, where the lower triangle has the same value, or symmetric to the upper triangle, okay, of a matrix. And then on the diagonal, you're going to have all zeros, because the isolation requirement of the distance function, if you have if you have an identical objects, then the distance between the identical objects are going to be 0. So the meaning of distance matrix is that, for example, let's consider an ith row and a jth column. It's simply, the meaning of that is the element at dij is the distance from the ith row, the object at the ith row, and the jth row, and you compute the distance, and that's going to be the element dij in the distance matrix. So in case of the diagonal components, obviously it's going to be dii, so distance from the ith row to the ith row. So obviously the distance is 0 by definition. So you always have a symmetric matrix that has the structure like this all the time when you compute a distance matrix. And if you don't have this structure, then your computation of distance matrix is wrong. So it almost sounds like a very trivial thing, right? Or the definition of distance matrix and the symmetry and the 0 terms and the diagonal component. It sounds very trivial, but when you actually write a code in practice, if you make a mistake, then your distance matrix is going to be messed up. And a lot of time, since this is so trivial, a lot of time people just don't even check if the distance matrix is in the right structure or not. But I've seen a lot of cases where maybe because of a bug or the way that the distance function is defined or whatsoever, the distance matrix is not actually symmetric, or some cases contains diagonal element that is non-zero. Okay, so you probably want to make sure all the time before to proceed with anything. Now, going back to the definition of the Manhattan distance, okay, so when p equals to 1, okay, this is a definition of a Manhattan distance, and especially when the features are binary, okay. So let's say you have a data set, and then the data points are actually some binary digits. Then the Manhattan distance is also called as a Hamming distance. So the Hamming distance is kind of an interesting distance that you can use to compute the binary sequence. So simply speaking, if the components are all binary, then the Manhattan distance is going to be simply just the comparison of when how many components are identical to each other. So if you look at this feature 0, 1, 0, 0, 1, 0, 0, 1, 0 for X, and the feature 1, 0, 0, 0, 0, 1, 0, 1, 1 for Y, if you compare them together, the first component and the second component are not the same. The third and the fourth are the same, but the fifth and the sixth are not the same, and then so on and so forth. There's a typo. This is 4. Therefore, the Hamming distance, I'm sorry, it is 5. Therefore, the Hamming distance is going to be the number of different components. I think I made a misstatement earlier. The number of components that are not the same is defined as a Hamming distance. If you think about the definition of a Hamming distance, since we're talking about a binary elements, when they're the same, it's either 1, 1 or 0, 0. So this part is going to be 0 when the two components are the same. When they're not the same, it's either 1, 0 or 0, 1. So in case of difference, you have always 1. So and that's about the within the summation sign, and we're basically just taking the sum over the entire dimension. So the Hamming distance happens to be just counting the number of elements that are different from each other. Okay. So that's the definition of Hamming distance. Here I throw at you another useful distance matrix. Well, to be rigorous, this is not a distance matrix, but here's a thing called a Jaccard coefficient. So Jaccard coefficient is also called as intersection over union because of the very definition of, the fact that the very definition of Jaccard coefficient is the count of elements within the intersection between X and Y divided by the count of elements in the union of X and Y. So, representing with a Venn diagram, if I have a set X and set Y, then the intersection is going to be the, this portion over here in Venn diagram. And then the union is going to be the entire area circumscribed by X and Y. So when the two sets are getting closer and closer and closer, and then becomes almost the same, like this, then the intersection is going to be the same as the union. So when X and Y are identical, then the Jaccard coefficient is going to be 1. When X and Y are disjoint, that's the situation where X and Y can be completely different, right? So then the intersection is going to be empty set, right? So therefore, the size of the empty set is going to be 0. And no matter what you have on the denominator, the Jaccard coefficient is going to converge to 0. Okay, so Jaccard coefficient is, in fact, a very useful metric to measure the similarity between two sets. So this is not, rigorously speaking, this is not a distance metric, but a similarity metric that sets, some value between 0 and 1, depending on how similar things are. So like in computer vision, for example, Jaccard coefficients are used to evaluate how accurate an object detection is. So let's say you have a problem of detecting a face in a photograph, right? And then let's say you have a ground truth label, which is a bounding box, and then you have the actual detection result. So then, when you want to compare how accurate that detection was compared to the, ground truth, you will have to somehow compute, how similar they are. And Jaccard coefficient is one of the popular ways of comparing the two bounding boxes. So simply you compute the intersection between two bounding boxes, and then compute the union between two bounding boxes, and then just divide the intersection by union, and that becomes a Jaccard coefficient. So you can see that in a lot of computer vision literature, you'll see this thing called IOU. Okay. So IOU is an intersection over union. So depending on the community, some people prefer to say Jaccard coefficient. Some people prefer to say IOU. Okay. So here's, again, the same Venn diagram, slightly prettier representation. So I'm going to skip this ahead. Similar to Jaccard coefficient, if you happen to be in medical imaging application, there's a thing called Dice coefficient. A Dice coefficient is pretty well. Let me go back to this previous definition. So there's a similar thing called a Dice coefficient. The definition is pretty similar. So basically, you compute the intersection between the two sets divided by the sum of x and y multiplied by 2. So pretty similar in terms of formulation, but rigorously speaking, there are two different things. But for some reason, in medical imaging, as opposed to Jaccard coefficient, people prefer this Dice coefficient, and this is in fact the same as the definition of an F1 score. So I just wanted to bring that up because I know quite a few of you are working in the area of medical imaging. So that's another very popular metric for comparing similarity. Okay. Now what we want to think about is, okay, so when you have some numerical representation of a feature, then a lot of time you can just employ one of those Minkowski distance families, right? You can either go with a Manhattan distance. In case of binary, you can go with a Hamming distance. When you have indeed a vector quantity, so you have a sensor measurement, for example, you have an accelerometer signal, then obviously the most physically meaningful choice is going to be Euclidean distance. So when you have a numerical, when you have numerical features, then computing the distance is oftentimes quite straightforward. But let's say you have strings. So you're comparing the similarity between tweets, for example. So people say a lot of different things on Twitter, right? And let's say, string X and string Y, those are, each of them is a tweet. And then what you want to do is to compare the similarity between the two. How would you do that? Okay. So one simple way, and this is not so practical, but just to promote our thoughts, one simple way is to, compute the Hamming distance between two strings. So let's say we have a string CGTAACG and then another string GATTACA, then we can measure the distance between the two by counting the number of elements that are not the same. So in this case, the Hamming distance is going to be 4. Right? Now, there's obvious problem. Nobody tweets at the same length, right? Everyone, tweets with a different length. So some tweets are short, so you have only 20 characters. Some tweets are long, so you have 200 characters. And in those cases, it's really hard to compare the Hamming distance, right? So that's first problem here. The second problem is, consider this scenario. We have AGA TTAC, and then for Y we have GAT TACA. And if you think about it, they are quite similar, right? They're quite similar, except that the ordering is kind of messed up. So we have like the same number of T's, same number of A's, right? We have 3 A's over here, 3 A's over here. And then we have, we have 1 G, and then we have 1 C, right? Now, and also, I don't know if you recognize the pattern, it is indeed just one permutation. So GATTAC, GATTAC is the same. In case of X, we have A in front. In case of Y, we just pushed everybody up by 1 row, and then A kind of went to the back. So it is nearly almost exact sequence if you think about it. Now, when you use a Hamming distance to compare these two, then the distance is going to be 6, because only one component is consistent, and then everything else is different by the definition of Hamming distance. So obviously, the Hamming distance is not a good metric when you compare strings. So for those kind of scenarios, there's this thing called a string edit distance. The idea of it is that when you have a string X and string Y, how many modifications would it be required to convert a string X to a string Y? Okay, so that's the idea. And for each of the modifications, it is allowed to make only a single character edit. Okay, so you can either insert a new character or delete a character or substitute a character with something else. Okay, so those are the only allowed edits. Okay, when you compute the string edit distance. Now, of course, there are many ways. There can be many ways, of converting one string to another, and we agree to use whatever is the shortest distance as the string edit distance. So let's say, I came up with a way to convert a string X to string Y in 4 steps. Okay, but then you came up with a better idea to convert string X to string Y only with 3 steps. Okay, and in fact, nobody else have found anything smaller than 3 steps. So then the string edit distance from X to Y and Y to X becomes 3. Okay, so that's the very definition of string edit distance. Now, I just want to jump directly into the example. So this is the same example that we saw a few slides ago. So again, GATTAC is repeated. Okay, only difference is A. Now, try to think how you would convert the string X to produce string Y. Okay, I'll give you a few seconds to think about it. All right, have you guys figured it out? Let's see. So in order to convert this into Y, convert X into Y, the first thing I want to do is probably get rid of A over here at the beginning, and then make it a GATTAC. Okay. Now the second modification is to add A at the end, right? And that's the only steps that you would need to convert from X to Y. You just need to remove A and then insert A at the end. So in the sense of string edit distance, the distance between the 2 strings is only 2, because you would only need just 2 steps of modification to convert a string X to a string Y. So if you think about it, this could be a better definition of the distance compared to the Hamming distance, because Hamming distance completely ignored the repeated pattern, right? And then in the Hamming distance sense, the distance between X and Y was 6. And that's, not so intuitive, versus in this case, the distance between the string X and Y is 2. And then the way that we derive this number is quite straightforward and intuitive. So we can argue that string edit distance is a better distance, right? Now, there's a problem. When you compute the string edit distance, you need to think about how you would implement this in a computer algorithm. Remember, you need to somehow compute this, right? You need to somehow let your computer to compute this, as opposed to you doing all the heavy lifting, right? So how would you implement this in a computer code? Is this straightforward? And remember, the string edit distance, we're going to take the minimum number of edits. So among many different ways of editing one string to another, we're going to take the shortest cut. And finding that shortest cut is obviously not a easy problem. And you may actually end up solving an optimization problem, like a combinatorial optimization problem, right? Because among many different ways of getting from X to Y, you'll have to find an optimal, the minimum number of edits. And that's the definition of the string edit distance. So if you think about it in that sense, Again, if you have a small data, then that's not going to be a problem. Okay. But if you have a large amount of data, the computational time to compute the distance is going to be significant. So is a string edit distance an important metric in the context of big data? Maybe not, right? Because you will need to solve this, NP hard problem to come up with the distance, which is quite expensive to solve. Okay. So the reason why I just threw at you some random, set of distance metrics is because I wanted you to think about the problem. Remember, always with big data, you have the curse of dimensionality. Okay. It's going to be fairly difficult if it takes a long time to compute a distance. In case you have a small data set, then you're fine. But if you have a big data set, then it's going to be quite difficult. And when I say this, when I say big data, remember, we're not just talking about the sheer volume. So we're not just talking about a big N. We're also talking about the big dimension, because variety is, another important component of big data. So which means instead of just, 10 or 15 columns, you may have hundreds of thousands of columns in your data. And if you have large D, then, you get to have a problem with computing, for example, Euclidean distance. Okay. So in case you have big D and big N, then Manhattan versus Euclidean distance, clearly, computational speed, the winner is Manhattan distance, because you don't need to compute any square root, or anything. You just need to compute the difference between the elements, right? And then just remove the minus sign, remove the negative sign. Whereas in case of Euclidean distance, you have to compute the square roots, and the squares, take the summation, and just so many hassles. Especially when you have a large D, then the summation is, right, defined by D. Okay. So when you have large D, then obviously you have to take the square of many, many, many components. And the slight difference, right? I mean, computing a square of a single number doesn't really take, even a millisecond. But, if you have large N and large D, then you can easily just, snowball into something really large. Okay. So the reason why I show you a lot of different, and randomly selected distance metrics is, first of all, to kind of help you brush up, what kind of distance metrics are there. You probably learned this from, a statistics class, or, whatever, or some other machine learning class. But, on the other hand, I wanted to give you a chance to think about the distance metrics from the perspective of big data. Okay. Because a small difference can make a large difference when you have large N and large D, right? So now that we have seen all sorts of different distance metrics, we need to start talking about how to apply this for, the actual data analytics problem. Okay. And informally, okay, we're going to take a look at two different problems. And then I argue that these two different problems are actually representative of, many of the practical problems that you're going to come across in the future. Okay. So many of the problems is going to, fall into either the first similarity search problem, or into the second all pairs similarity problem. So the first problem here is a category of problems where you're given a set of objects. So you have many, many, many objects. Okay. Now you have a query point, which I'm going to use this cross to indicate. And the goal is to find the most similar object in the data set X to the query problem. So this is sort of like a K and N problem, right? So K and N is one obvious example that falls into this first type of problem. The second type of problem is all pair similarity problem. So in this case, you don't really have a query point. What you're going to do is to basically take all possible pairs, right? There can be many, many combinations of pairs within the data set like this. So you're going to take all the pairs, and then for each of the pairs, you're going to compute the distance. So the result of this is going to be actually a distance matrix, right? So those are the two common problems. Now, we're going to talk about these two different problems and then try to expand this, try to think about this problem in the context of big data. Okay. So let's talk about the first problem. Assume that we have a distance function that is defined as d. Then the similarity search problem over here, if you think naively, then what you can do is to compute for a given query, you compute the distance from query to x, right? The ith object in the data set. And then you repeat this for all I. And then after doing this, you're going to have a vector where the elements are the distance from each of the objects. So dq to x2, dq to xn, right? Sorry about my drawing. So as a result of computing this, you're going to have a lengthy vector. Now, once you have this vector, then obviously what you can do is to take the minimum. Okay. You're going to take the minimum. So let's say the ith element was the minimum. And that, the element that corresponds to that minimum is going to be the closest neighbor. Okay. So in case of a small data problem, you can simply just construct this matrix and then, compute whichever is the minimum, right? And that's going to be the closest element. So not an issue here. But now, let's say you have a really large n. What are you going to do? Right? The second type of problem, okay, we're kind of jumping back and forth to give you the taste first. Again, we have a distance function d defined on the data set. Now, the naive solution for all pair similarity problem is to simply construct a, distance matrix. So our distance matrix D is going to have an element at ith row and jth column, which is defined to be, just the distance from the ith object to the jth object. So simply speaking, your naive solution is going to be to compute the distance matrix, and then you're going to find the one that is the most similar. And practically speaking, you don't really have to compute the full distance matrix. You only need to compute either the lower triangle or the upper triangle because they're symmetric, right? But nonetheless, what you need to do is to compute the distance matrix. And, after constructing a distance matrix, you can simply just find the one that is smallest number. Again, when you have a small data problem, then the size of the distance matrix is not going to be too large. So there's no issue here. But let's say you have a large data problem where you have 100,000 rows, then the distance matrix is going to be 100,000 by 100,000. When you have 1 million rows, then the distance matrix is going to be 1 million by 1 million. So you're going to have a situation even where, computing, aside from the time that is required to compute a distance matrix, you're going to need a really, really large memory on the RAM, which is not quite available, right? So we have a situation here, right? We may not even be able to create an array, create a matrix variable on the RAM. And, if we cannot create even a memory space, we cannot even allocate a memory space for storing a distance matrix, how are we going to approximate the distance matrix, right? So those are the two situations. So obviously these naive solutions are not so good, right? So for the first similarity search problem, I already mentioned that, the computing, we need to compute a vector simply, right? And then in order to compute the vector, for each of the element in the vector, we basically need to go over, the total d dimensions, right? And then we have to do it n times. So the complexity is going to be nd, right? So it doesn't really sound terrible because it's a linear complexity. But when you have a large, set of data, then, even the linear complexity is not so good. So, the goal really here is to beat the linear time algorithm, which is quite, difficult. The second problem here is that, again, the same thing. We have n by n matrix, and then for each of the components, we have to compute d times of, multiplications of a number. And since we have total n square elements, the total complexity is n squared d for all pair similarity problem. And of course, we can, make it a little more efficient by just calculating only the lower triangle or the upper triangle. But anyways, it's a quadratic time. And in the context of big data, quadratic time is prohibited for almost any situation. Okay. So what are you going to do? So that's something that I want to discuss today. Okay. So as a warm-up exercise, let us just, think about this. I was going to put you guys in the breakout rooms, but since we're kind of, a little bit slow at the pace, so let me just do this all together. But let's think about it. Okay. So we have data set X, okay? And then the dimension here is d equals to 1. So it's a one-dimensional set of points. So 5 is our data sample over here. 9 is another data sample. 1 is another data sample. So they're all kind of, very simple data set. Now, when you have these set and you're given a query point, which is q equals to 6, how would you find the nearest point q in X? Okay. So that's essentially the question over here. Now, if you think about it, of course, the naive solution is to just compare one by one. So compare 6 with 5, compare 6 with 9, compare 6 with 1, and so on and so forth. But we don't want to do that, right? We just talk about it. That's not a good solution in the big data context. So you probably want to have a better way to do so. Now, here's almost a spoiler. The answer is, you need to sort the data set and index them in a manner that it is easier to find where the data point is. And once you have that structure, you can do a binary search. So what I mean by that is, consider this kind of a spatial representation of the data set. So we have, all the data points in the data set X distributed over a space, over a one-dimensional space, which in this case is just a real number line, right? Now, what you can do is to kind of, before, accepting queries in offline, you can do some heavy lifting beforehand and then get ready for some random queries that will be coming in the future. So what you're going to do is, here's one idea. So let's say, for a fact that your numbers are distributed between 0 and 26, right? So you know that 13 is kind of in the middle. So then what you can do is to construct a binary search. Construct a binary tree, meaning that with respect to 13, okay, we have elements on the left, meaning that number is smaller than 13. And then we have elements on the right, meaning that elements bigger than 13. Now, if you look at the elements on the left, which are 1, 2, 3, 5, 7, 9, 11, right? Then something in the middle is roughly 6. So again, you can partition the one-dimensional space with respect to 6. So things that are on the left-hand side of 6 and things that are right-hand side of 6. And on the left-hand side, we have 1, 2, 3, 5. On the right-hand side, we have 7, 9, 11. So similarly, we're going to do the same thing on the right-hand side of 13, which in this case is what? Roughly 19, right? Would you agree with that? Yeah, let's just go with 19. So then 19 is right in the middle of the later half of the distribution. And then on the left-hand side of 19, we have elements 14 and 17. And then on the right-hand side, we have elements 21 and 26. So you can, keep repeating this. Okay, I'm going to show you an example. So, continuing on this 19th side, on the left half, we have 14 and 17. So, 19 and 13 in the middle is what? 16. So with respect to 16, now we have 14 and 17. Okay, those are the data points. And then on the right-hand side, we have 21 and 26 with respect to what? 22. Yeah, I'm just being sloppy here, so I might not be precise, but okay, let's just agree on that. So then, you can do the same thing on the left-hand side, and then, you can keep expanding the binary tree. Okay. And at the end of the day, you're going to have this kind of a tree structure that you can compute in offline. And once you have this tree structure in offline, then in online, when a query comes in, okay, the search becomes fairly easy. So let's say, like in this example, the query point was 6. Okay. So then in that case, what you're going to do first in this binary tree is to compare 6 with 13. Is 6 on the left of 13 or on the right of 13? It's on the left, right? So that comparison is quite easy. So then you go to the left half of the binary tree. And in this case, it's kind of a trivial example, but let me just, continue here. So in case of 6, then what do we have? 6 is basically the same as 6. So there's an equal chance that, there's an object on the left-hand side and on the right-hand side that are closest to the query point. So what I'm going to do is to visit left-hand side, and then, do the similar, repeat the similar logic. And then let's say, at the end of the day, I, finally reach to conclusion 5. And then I do the same thing because, they're a tie. So then I kind of follow down the binary tree, and then I found 7 to be the closest neighbor on the right-hand side of 6. And therefore, 5 and 6 over here are the candidates for the closest neighbor to the query point. And in fact, the distance from 6 to 5 and the distance from 6 to 7 is the same. So then both of them can be returned as a nearest point. Or if the user wants just one point, then you can roll the dice and randomly select either 5 or 7. And that's basically going to be the way that your algorithm is going to work. And by doing so, we don't really compare 6 with all the numbers in the data set. We only compared, against a few selected numbers. So the computing time is going to be actually way better than the linear search. Okay. To give you another example, so instead of 16, let's think about 22. Okay. So now 22 is the query point. Is it bigger than 13 or smaller than 13? It's bigger than 13. So with that, we're going to go to the right-hand side of the binary tree. Is 22 bigger than, well, why did I choose 22? Let's go with 23, okay? So let's say the query point was 23, and 23 is bigger than 13, so you go on the right, and then 23 is, the query point is still bigger than 19, so we go on the right, and then 22 is bigger than, sorry, 23 is bigger than 22, so we still go on the right, and on the right of 22, we have 26, okay? So as such, instead of, searching through the entire number, we just compared, the query point against 13, 19, 22, and 20. Yeah, that's it. So we only compared against 3 numbers as opposed to entire elements in the data set. So that is, in fact, one of the strategies that people are using in a high dimensional space as well. So we saw this example from 1D. Now we're going to see that this can be actually expanded to a larger dimension. Now, from this 1D example, one lesson that, I want you guys to learn is that by doing some pre-processing, pre-structuring of the data, you can actually dramatically improve the computational time as opposed to the naive linear comparison algorithm. So this pre-processing, okay, is sort of a partition of a space. So you have a one-dimensional space, and then you somehow partitioned the space into a binary tree, right? And that's kind of the idea that we're going to, apply to a larger dimensional space as well. Okay. So one of the most popular algorithm that is based on this idea of constructing a binary tree is what is called a KD tree. Okay. So KD tree is an algorithm that works fairly similar to what we just saw. Okay. So we're going to take a look at the 2D example first. But before that, in order, just to get started with the conclusion, the pre-processing time is definitely, larger than, just a linear time. So it does take some overhead in terms of preparing data. But if you look at the query time, we have a square root of n. So this is obvious. This is obviously lesser time than the linear complexity. Okay. Now, how is that possible? Here's an illustration of how KD trees can be constructed. Okay. So consider these 10 points. Okay. These 10 points are our data samples. And what we're going to do is to construct a KD tree by basically splitting the space, partitioning the space into smaller binary partitions. So what I'm going to do is, let's set up a virtual sort of a coordinate system. So I have a horizontal coordinate and then the vertical coordinate over here. And along the horizontal coordinate, first of all, I'm going to find the median. Okay. So the median of this points horizontally. So what I mean by that is you're going to project that conceptually onto the x-axis. And then within this projected distribution, what is the median? So that's roughly P5 over here. So that's going to be my first partition. Now, in the next step, what I'm going to do is I'm going to visit the left partition of the space, and then I'm going to find the median, okay, along the vertical direction in this time, okay, because we just did the horizontal direction. So to be fair, now we have to do it vertically. So I'm going to find the median and then draw a partition. I'm going to do the same thing on the right-hand side. So again, vertically, I'm going to find the one that is in the middle, and that's going to be my the location of my second partition. So roughly speaking, we have P2 in the middle, and then P7 in the middle, and that's going to be my next level of partition, which is represented as L2 and L3. Now, in the next round, what I'm going to do is I'm going to visit this partition and this partition and this partition and this partition. Okay, and this time I have to, find whatever is in the middle on the horizontal direction. Okay, and as I keep repeating this process, okay, so for the first time you draw the partition line on the horizontal axis, and then you do the partition on the vertical axis, and then do the horizontal axis, and then vertical axis, and then as you repeat this process over and over again, then you're gonna come up with this sort of a partition, and that in fact is represented as a graph that looks like this, right? It's a binary tree. So L1 is a first partition that splits the data set into left and right. And then L1, the reference for L1 is P5, right? That was the one in the middle. And then on the left-hand side, we have this partition over here. And then the second level of decision line was the one over here. And then the reference for that is P2. And the same thing on the right-hand side, L3 was the partition line, and then the reference for that was P7. And then as you repeat this process over and over again, then you're going to have a binary tree that looks like this. And then, the treatment for the final, the leaf nodes is basically, in case of this partition over here, after you split the space with respect to P4, there's nothing on the left-hand side and the right-hand side. So we have just empty blanks. In case of P3, okay, the level, the L5 partition line. On the right-hand side, you have nothing. On the left-hand side, you have P1. So you just, put that as a leaf node. And then on the right-hand side, we have an empty set. So as you, do this process, you can construct a binary tree that looks like this. Now, given this binary tree, then what you can do is, okay, let's say I have a query point here. So that red dot over here is my query point. And I'm going to call it Q. Okay, so the Q comes in. Instead of comparing Q against all 10 points, now what you're going to do is to first compare it with P5. Is it on the right or left? It's on the right. And you don't have to really compute the all dimension because P5 is along the horizontal dimension, horizontal axis. So you don't really have to compare all coordinate values. You just need to compare the first coordinate value. And if the first coordinate value is bigger than P5, then you're going to go down to the next level of decision tree. And then the next level of decision tree says the query point is bigger than P7 because it's above, right? So then we're going to go to, well, I think, yeah, I think I should have actually changed the, swap the location of L6 and L7, but just bear with me. So, you know, Q is bigger than P7, so we're going to go to then the L6 side, right? And on the L6 side, you're going to compare it with what? With P9. And then is it on the right or is it on the left? It's on the left. So it goes down to this space over here. Okay. And during the process, we never really visited even P2, P4, P3, P1. We never even talk about it. Same thing with P6, P8. And without visiting all the points, we already have some candidates for the closest point. Now, in KD tree search, what we're going to do is then to, you know, go back up. Okay, we're going to crawl up from this leaf node of the binary tree, and then we're going to start comparing the distance. So obviously, the leaf node is an empty node. So there's nothing that we can compare the distance against Q. So we're going to go up to the P9 node. And what we're going to do is to compare the distance, calculate the distance from Q to P9. Okay. So we just computed the distance from Q to P9. So I'm going to just call it D9. Now, we're going to, you know, curl up again. And then we're going to compare the distance with P7. So we calculate the distance from Q to P7, and that's going to be my D7. And then I'm going to curl up again, and I'll compare the distance from Q to P5. And that's my D5. And if I crawl up one step further, then I, you know, basically pop out of this binary tree. So then as a result of this process, we have only 3 distances. But that's enough because we know that Q lives in this partition. So anything actually that's beyond this partition doesn't need to be compared, right? Because Q isn't there. So why would you, for example, bring a point in some other partition like this and then compare the distance with Q, right? That's unnecessary. You can limit your search within the partition. And in that way, you know, we produce 3 distances as opposed to all 10 distances. And among 3, finding which one is smallest is not a big problem, right? You just compare them. So that's kind of the value of KD tree. Okay, you first, no matter how long it takes to construct a KD tree, you first construct a KD tree, and that happens in offline. But once you have a KD tree, then what you need to do is then in the query time, in the online, right? Whenever query comes in, you just simply quickly go through the binary tree by only comparing one coordinate values at a time. And then based on that trajectory, you're just going to compute the distance from Q to each of the nodes. And then you're going to compare only the nodes that are touched by this trajectory. So in that way, you can save a tremendous amount of computational time compared to the naive linear search algorithms. And you can easily see that this is going to be very useful when you have a large data set, right? Because then you don't really have to, let's say instead of 10 points, now you have 10 million points. So instead of then, going through all 10 million points, you can, just trace down the binary tree, and then whichever, happens to be in that, trajectory of that tree search, right, is going to be computed. And, only within the ones that are in that trajectory, we're going to compute the distance, and then we're going to compare which one is the closest. So in that way, you can dramatically improve the search speed for a, the first type of similarity search problem. Okay. So with that, we're going to continue talking about this kind of approaches. In fact, so far I said KD tree is an amazing method, but there are some situations where KD trees, are not so suitable. So we're going to actually talk about some other similar methods like KD tree that can be applicable to large data problems on next Tuesday. Okay. So, but takeaway message from today's class is obviously, the idea of pre-processing and partitioning the data beforehand. And then in the query time, you just, use that pre-structured data to facilitate the distance computation. Okay. So with that, thank you very much, guys. And I'll see you on Tuesday.